So we worked quite a bit in the lab on metadata private communication. And so the motivation for this is, or the way we started is basically with this problem, right? So Alice wants to communicate with someone. So of course she has many ways to do so, and it might be encrypted, but the communication metadata, meaning whom she's communicating with and when, that's kind of available for anyone observing the traffic and might be sensitive. So we wanted to hide that. And of course, this is a pretty well-known problem. And kind of many solutions that were proposed. And I think, kind of at very high level, you could maybe place them in several buckets, right? So on one end of the spectrum, there's Tor. Pretty sure many of you heard of it. It's probably the most kind of common system. It's very efficient, but it has some some assumption on its servers and on the network. It doesn't resist a global adversary, so it provides some. It tries to hide communication metadata and is very generic, but it's not like a provable, like a property you can easily prove. And then the systems based on mixed nets. By the way, if anyone has anything to ask or say, just yeah.
Can you explain what does it mean that Tor does not resist global adversary?
Yeah, so Tor is so performant in the sense that it tries to not delay traffic, right? So, okay. Yeah, so basically you see someone sending a message and another person receiving a message, and you can sort of correlate those, right?
You're saying, but if you use the timing information to infer, then that means it does not.
Right. So even though in Tor you go through several servers, just by correlating times, you could figure out who's communicating with whom. And then there are mixed-net-based systems. So they do resist this global adversary. They do resist someone who's monitoring the network, but they require trusted servers. So maybe not all servers are trusted. Maybe there's just one server that needs to be good, right? But there has to be one server that is honest in the system. And those systems add more latency, generally speaking, but scale pretty well with the number of users, meaning that the server's work is linear in the number of messages it processes, or the number of users in the system. And then maybe the best we could hope to achieve in terms of privacy. There are systems based on private information retrieval. These are relatively recent. And here, there is no trusted server. There's some assumption on the computational capability of the attacker, but the server is not trusted. It resists the network adversary that monitors traffic, but the server has to do way more work. So specifically, when we kind of go into the details, we're gonna see that they don't scale that well. Specifically, in these systems, the server has to do quadratic work in the number of users. Okay. So this work basically kind of reduces the load on the servers, the computational load, and instead of doing quadratic work, we do like users to the 1.5. So asymptotically speaking, it is more scalable, and we're going to see how this translates into performance in practice too. Yep.
there are works which are doing code distributed PIR, but they are not assuming some servers are trusted. So this
right. So
same name.
Okay, yeah, maybe we should have named it kind of differently. But yeah, what I'm referring to is we're gonna work in the same setup where the servers are not trusted, or there's no trusted person in the system except for the person sending the data or receiving the data, right? And that's a good comment. Okay, so what is it that we do? So basically, in this work, we're going to take the server, the server's work, the things that it was supposed to process, and then let workers do it for us. And in the context of our messaging system, those workers are going to be other clients in the system, right? So essentially, the server is going to kind of distribute jobs to these clients, and then each client has to respond with its like tiny portion of the work it needed to do. And that lets kind of the server avoid the heavyweight computation. It removes or kind of makes the bottleneck computation better. It lets the system scale better. Intuitively, the more users you have, the more processors you have. So even though you have more load, you also have more people kind of handling this. And then the main kind of maybe the main thing that we had to handle is that now those clients, they need to be untrusted. So clients are more likely to give us kind of bad responses. Right? They can cheat in the computations that they do. So we need to somehow deal with that. Right? When you have a system and it only has one server, right? Then okay, maybe you sort of trust the person deploying that server that server is going to be up and running, for example. But clients, and if it responds honestly, hopefully, like, at least for availability. With clients, like let's say you have millions of clients in your system, it's very likely that, even more likely that one of them is going to be malicious.
It's sort of like a peer-to-peer sort of flavor, right?
So it's not really peer-to-peer because we're going to use this server to distribute all the jobs to all the clients, right? So clients don't directly communicate. We were considering having a variant where it's just the clients do kind of communicate amongst themselves mostly, which could be more scalable, but then we weren't sure if it makes that much sense in terms of deployment. Like we weren't sure, okay, so how do you do like field discovery? How do you connect to other clients? So we thought we kind of stuck with this.
If actually clients are doing the heavyweight work, then what did you mean by the amount of work on the server is user 1.5?
So the server still has to do some things.
Oh, so
unfortunately.
Okay.
Yeah. So it does. Okay, yeah. So most of the kind of cryptographic calculations are now done on the client side, and the server has to do some work to validate the clients. So that takes a bit of. Yeah. Okay. So here's our communication model, right? And it's not unique to this work. Basically, in all these PIR-based systems, you can imagine there's one server and users read and write messages through that server, right? And our adversary can monitor the whole network, and it can also control the server itself, right? And the other clients in the system. Okay, so our goal is to hide whether two users, Alice and Bob, communicate, right? Despite this kind of strong adversary model. They can control basically anyone who's not Alice and Bob. Yeah.
So you're doing communication between the different clients, or you're doing PIR?
So
you're using PIR?
we're using PIR. So I'm gonna. So the way this works, this is kind of maybe the slide that explains it. You could imagine a user submitting a message, writing a message to the server. The server stores it in its database, and then some other user submits a PIR query that reads, kind of privately reads a message. Okay, so this is basically what we're going to do is we're going to split time into epochs, and in every epoch you kind of decide which other body you're going to communicate with. Then each user is going to submit a PIR query, which I'm going to kind of in the next couple of slides, I'm going to explain exactly what this is. But essentially, this is what indicates, or it doesn't indicate to anyone, but this is what lets the server compute the response for that user and read messages from their body, the body that they chose, and the query is dependent on that friend. So once per epoch, a user gets to choose which other person they're going to communicate with. They're going to send a PIR query, which the server is going to cache, and then it's going to use the same query through the epoch. And in every epoch, we are going to have multiple communication rounds where each user is going to send a message, store it at the server. Then the server is going to evaluate PIR queries against this database and return the responses to each user. So essentially, each user now gets to read one message per round from the friend that they chose at the beginning of the epoch.
But when you write, the main box of each user is well defined.
So
everybody knows what is. If I want to write to Bob, then I should know Bob's entry in this PIR.
Yeah, so that's a good question, right? So how do you know where to write, basically, right? Yeah, so the idea is that it is at the beginning of the epoch, you sort of the server kind of arranges mailboxes to everyone, and then there is an even, like there is one round that lets you kind of know which mailbox is going to be the mailbox of your peer. I don't really get into that sort of. There's another protocol that does dialing, and then users can exchange just this particular thing. But you can imagine, like, even. Yeah, so we assume if two users communicate, they have a shared secret somehow out of band. A shared secret somehow out of band, right? So maybe I met Alice. We exchanged something, and this maybe is an even harder problem to do online, right? So.
But you didn't share the mailbox. It's not like you know.
No. You don't really share the mailbox. No. But what you end up doing is you do this keyword PIR that you know this sort of protocol where you sort of read the index of the particular body at the beginning of the so okay. So then what happens? But for us, I guess we just assume, okay, I know the mailbox where I'm going, or the address of the message which I'm going to read from. And then I'm going to split my epoch into rounds, and every round, every user submits a fixed size message. So it has to be constant size to not leak any information, right? Yeah, I think we touched on that. So, and then the server just evaluates PIR queries against the database. So, okay, so what is this PIR protocol that I've been kind of talking about, and how do we use it here? So I'll just use kind of maybe the easiest version, which is basically we look at PIR as if it were a matrix, kind of an instance of matrix multiplication. So the server takes its n its database of messages. Let's assume there are n messages, and then it arranges it in a squared matrix. Now each client is in the query submits a vector, which is a one-hot encoding of the column in this matrix where the message they're interested in actually is, right? So this query is going to be a full-size square root of n vector, right? A column vector. And it's going to have zeros in every location except one location where there's one, and that location is the index of the is the index of the column where the friend writes their messages. Okay.
Are you also covering this entities writing to messages, or you're only focusing on how do you retrieve the messages?
So I'll focus on how do you retrieve. I mean, I assume, or I kind of abstracted it away. Writing is kind of simple. You basically have a session with the server. You have your mailbox, and you just tell the server, okay, here's my message, right? And it's encrypted with your buddy's key or with the shared key that you have with your friend. So, but it is treated as if it were like a plain text message.
Right, but
for purposes of PIR.
The mailbox is the recipient, right?
No, the mailbox is, so, okay, maybe I should have said that. So so let's say I'm a user of the system, right? I get an allocation mailbox, right? And then I write to that mailbox. So it's not secret to the server. Okay, it sees Bob, and Bob is writing to the mailbox that the server allocated to. The kind of the privacy sensitive part is when Alice wants to read from Bob's mailbox, and that's why you need the PIR to hide this. The read is sensitive. The write is kind of like, okay, everyone writes.
The user can write one message in the mailbox. So
right. So you don't get to all these things, but the rate is fixed. Everything is very deterministic. So if you just look at the writes, there's basically nothing nothing privacy leaking going on.
Writing in the mailbox, which Alice would know
to read from. Yeah, right.
Basically, you hide from the server the fact that the reader of your mailbox is Alice.
Exactly.
If you want to communicate with more people using this, you could use the same mailbox, but
you could
not be able to read. But that means that when they try to read, they will get garbage.
That's so. Unless they share the key, I guess. With but yes, then they get garbage. Then
but you can put whatever key management you want.
All right. So maybe you have a shared key with like a group. You could do that.
Good. If you want to communicate with a group,
right.
If you want to communicate with multiple groups, you need to allocate a separate round for each of them.
Exactly.
And they will need to just check
a separate epoch actually, because I guess in every so you could do separate rounds, and then some rounds you get garbage because you wrote a message for Alice and not for Carol. Yeah, right.
And you will need to read it, but can you read in the same round for multiple mailboxes or only for
no, just one mailbox. So you send one query. That query is left there for the entire epoch, and in every round the server has to evaluate that query against the database of current messages. So
and what you said about keyword PIR is like the mapping from keywords to integers, the super all of that.
Exactly. So the server allocates the slot in the matrix basically.
To be sure, right? So one column belongs to one user, right? So say for instance, if I'm a user, I have one column that belongs to me. That is well known, right?
No, what belongs to you is the mailbox, which is one cell in this matrix.
Oh, it's one cell.
It's one cell.
Oh, I see. So you curate it in terms of column, but you're actually only reading a
right, because in this Yeah, right. So I didn't want to get, like, you could do this recursively too and get even better savings, but in this variant, so what ends up happening is the server runs this kind of matrix vector multiplication for each query. And if you kind of sort of throw the resulting vector at the bottom, but what you can see, okay, so you multiply a matrix by a vector, so the result is a vector, right? And this vector, actually, if you do the math and you use this PIR, one of the reasons it's expensive is not only the quadratic or the cost of the server processing the entire database for every query, but also the fact that it relies on homomorphic computations. Right? So this encryption has to be homomorphic in order to do this evaluation. So basically what happens is the client, and maybe I'll kind of go back to this previous slide. So the client creates the query vector. To do that, they choose a public key or a secret key and a public key pair in this homomorphic encryption scheme. And this homomorphism lets the server calculate the resulting vector, which is encrypted by the key that the client chose. It's going to be encrypted for the particular client, and then the client gets in this kind of basic PIR protocol, the client gets a vector, which is the column in the matrix where the message they wanted to read is, and then they can decrypt the entire column. They basically toss anything except for the message that was interesting to them.
And I guess a batch PIR is not helpful to you here because the probability of, like, if I wanted to read multiple messages, them being in the same column.
Yeah, that's like more difficult to do. One thing that is helpful and we do use is there's this idea of compressing the query. So if you're already kind of using homomorphic encryption, right? So this encoding of sending a full size vector, which is basically all encryptions of zeros except for one place where it's one, is kind of wasteful. And so you can think of it. You can compress this a little bit further and have someone expand it using the homomorphism properties. So this is something we use. Wasn't invented by us. Okay. So then if you wanted to do this, like, okay, so we have a matrix vector multiplication if we have more than one client, right? So let's say we have n clients in this example, right? So now we have n of these column vectors, and the server evaluates basically the product of these two matrices. One matrix is the database, and the other matrix is the ones that where the columns are the client queries. Okay. So the main problem here is that the server actually has to calculate, or it needs to process the entire database for each query. Right? So when you do this server database client query product, this requires processing the entire server matrix.
So basically, the offline cost or online cost.
So this has to happen. This happens online. So basically, in every communication round, the server database changes because it has new messages, and now the server has to basically redo this multiplication. Yep. So okay, so this is unfortunate, and the reason for this high cost for these PIR based schemes. Okay, so now we want the clients to do most of the work. So how the way we're going to do this is we're going to assign clients into groups, and basically we shard these matrices in two ways, right? So all the clients in this group receive the same shard of queries and different rows in the server's database. Okay, and that lets and that lets every client calculate a bit, like a small part of the resulting matrix, right? So for efficiency reasons, we're using the kind of the compression here that I mentioned earlier. So when someone submits their PIR query, it's compressed, and then the server sends it also compressed to the clients doing the work. Okay, so at the start of every epoch, every client gets a bunch of compressed queries, they expand them, and then every round they receive a row from the database, and then they evaluate all the expanded queries they now have against this row, basically. Okay, so I guess the first thing to notice is that in terms of safety, right, so do we expose more information when we do this? And this is safe, and kind of you can maybe intuitively think of it as in terms of reductions, right? So the server in standard PIR doesn't learn anything about whatever the user who sent the query cared about. And so now that the server kind of split his view and gave some portions of it to clients, he couldn't have taught the clients something new. He didn't know anything to share from the beginning. So this version of PIR also leaves the clients oblivious to whatever they process. But the main challenge here is availability or liveness. So those clients, okay, they're oblivious to whatever they process, but they can also return bad responses. So they can just cheat. They can say that they did some computation and then send something else, not do the work, basically. And like one intuitive thing we were thinking at the beginning is, okay, we have this shared secret that I mentioned earlier between Alice and Bob, and they want to exchange messages. So of course we can authenticate the messages themselves. Right? So whenever Alice deposits a message, she already encrypts it. Let's do encryption and authentication. Why not? Right? There's this short MAC now. And when Bob reads the message, if some client cheated and they get the wrong message, then they see it. They obviously see that the MAC is invalid, and they can kind of declare this message as bad. And first of all, they discard the message, but then they can also maybe complain to the server and have the server remove that client. The problem is that once this sort of mechanism is introduced, right, if you complain, then the server learns that, okay, you actually wanted to read some message that is corrupt. Right? So maybe the server corrupts some cell in this matrix themselves, and then see who complains, and that's the reader. So you can't really complain, and if you don't complain, then this bad client can just keep on corrupting the responses for everybody.
If you complain, how do you know which client actually corrupt?
Well, I mean, you complain, then I don't know exactly the mechanism that would result in this investigation, but complaining by itself is a yeah.
But it's just not so sure if you do complain, how would it allow the server to identify?
Well, the server can repeat the work, basically. So one thing that you could do, right? So maybe the most obvious thing is the computation the client does is deterministic. So the server just can repeat the work and see. Let's say you repeat it even for all clients, just to remove the bad ones. I mean, let's say you are willing to pay the price, but you can't even complain. That's kind of like the entire point of privacy. So okay, so we can't complain. So instead, what we're going to do? Yep.
Just curious, did like the client
sends a bogus complaint and spam the server and makes server recompetes a lot, probably the DDoS issue.
Yeah, I mean, maybe. So the client complains, and then the server does all the work, learns that it's a valid point, right? Then learns that all workers were fine, and it's actually the person who complained that was kind of invalid. So they kick them out, maybe. But like in terms of like the natural flow of things, it's risky to do. If you wanted to do this, then you would let the server essentially break the privacy of the system. Okay, so instead what we're going to do is we're going to have the server check the responses that it gets from clients, these partial computations of the PIR, to make sure that they actually did the work correctly. Okay, so how can we do this efficiently? Right? So okay, maybe we don't want to. Before I mentioned, oh, maybe the server does the entire thing, repeats the calculation and sees who was bad. But there's actually an even more efficient way to do it. So luckily, if you view this PIR variant as matrix multiplication, then you could efficiently validate the product of two matrices, right? So I guess they even teach it, I think, in like basic algorithms class, right? So the Fevald's algorithm lets you check the product of two matrices. And the trade-off here is that there's a small chance of error, right? But you could repeat this calculation and basically drive this error probability to 0. Okay, so how does it work? Well, the server basically chooses a random challenge vector, and then it checks equality between two things, right? So essentially, if this result is correct, if m times q is r, right? Then if you multiply r by this column vector that the server randomly chose, and then if you first multiply q by this column vector and then multiply from the left by m, then that should give you the same result. Right? So they should be equal. Okay, so this is sort of nice, and the reason for why this is efficient is because you never multiply a matrix by a matrix, right? So this is a matrix vector multiplication, and this is a matrix vector multiplication. The result is a vector, and then you multiply again a matrix by a vector. So it's more efficient to do. Maybe one tricky part is that our server doesn't. Yeah, you want to ask something? Oh, no? Okay. So the tricky part is that these are all ciphertexts. The server has no secret decryption keys, right? So it can't actually decrypt the result. So in order to detect that these are equal, like in order to make this check, the result has to be an actual 0, like not an encryption of 0 or anything like that. It has to actually be 0. So,
and isn't there another problem that, like, this is guaranteeing you with overwhelming ability that random things, right, that the matrix matches on random elements, encryptions need not be distributed randomly either. Or is that not a problem?
so I'm not sure that I got the question.
So right, the guarantees of this are right that the right for random elements, these map to the same thing, right? But you can't have a very small
So the matrices don't need to be random for Frivalds to work.
No, but C does.
C does. That's right. So the server chooses this. So the server wants to validate all the workers, basically. What I want to do is to make it so that the system is available, or like the server can catch the bad workers, right? So this is like in normal. Let's say you didn't distribute at all. The server was down. The system is down. So same thing here, right? So it's the server's job to check the clients. Yeah. Okay. Okay, so this is this absolute, like having an actual zero instead of an encryption of zero is one thing, and the other thing is that this kind of algorithm works with full matrices, right? But we keep receiving responses from, this is more of a performance issue, right? We keep receiving things from the responses from clients, each client at a time. Or like they might come at various times, and we want to validate the client as soon as we receive something. So we have this variant. So to address this latter problem, we have this variant of Frivalds, where we can cache certain things and maybe calculate things ahead of time so that we can check each client individually. And this takes advantage of the fact that every client has a full row of the kind of message database, right? And then it evaluates that row. It multiplies that row against columns of user queries, like full columns, right? So this lets us kind of do some optimization. So first of all, the server can choose the random vector ahead of time, and then they can multiply it by the query matrix at the beginning of this epoch, right? So that's nice. The other thing is that, okay, you don't have to wait for the client's response, the worker's response, right, to calculate some parts of it, right? So we already know which row you gave to each client and which queries they handle. So you can make this other calculation ahead of time because it doesn't depend on the response, right? And then the last thing that is left is doing this calculation, the other side of the equation, or this R times C, whenever responses arrive. Now a client response is actually a row in this. You could imagine it being a row in this result matrix R, and so you can essentially multiply that resulting row by the challenge vector, right? So this gives you one element per client, and also the other calculations, right? So when you do this QC, you get the vector, and then you do this calculation. You multiply two vectors, you also get one element, and so you just need to check for this equality. Okay, so this sort of does a bunch of work ahead of time, and then as soon as the client's response arrive, you can check each client's response individually. Now the other point is that for this to work, we need associativity in the ciphertext space. So this is about getting to this absolute zero. So whatever, let's say you use the fully homomorphic encryption scheme, whatever scheme you were using, you're guaranteed for this check to work if you could decrypt the result, right? So you can always make this calculation. You can always check whether if you subtract the left-hand side from the right-hand side here, it's supposed to give you 0. But you might get an encryption of 0. So in order to get an actual 0, that doesn't work with every encryption scheme. So in particular, when we started, we used the BFV scheme that others have used in these PIR-based systems that we were trying to expand. And apparently that one doesn't quite work. So it doesn't have this property. It gives you, it wouldn't give you an actual zero that the server could detect, because in the encryption process, they're using rounding. So they do a bunch of calculations and then they round the result to some close element, I guess. And so it didn't quite work. So we ended up using BGP, which actually does have this property. Okay, and another nice thing is that you can have an incentive mechanism on top of it, right? Because the server detects, so as soon as a client response arrives, the server can check that response, the particular response, and then if that response is invalid, they can just boot the client, remove them from the system. So you can sort of have certain kind of enforce certain things, like, okay, a client can only participate in the system, can only read and write messages if they actually handle the previous round correctly. All sorts of things that kind of motivate clients to work correctly if they wanted to use this system.
You're not protected against the server, of course, claiming the server is not.
No, if the server is, I guess if the server is malicious, they can just remove. We have no guarantees on availability, right? So they can just take the system down, basically. They all particular users, they can, yeah. I guess we already had the server allocate cells in this matrix for each user, so we didn't care, you know. Like, okay.
So if you did, I guess, do all malicious PIR schemes require private reprocessing?
Do all malicious? What do you mean by malicious PIR schemes?
Where you can detect, like, actively secure PIR schemes.
Mm-hmm. Well, so usually in these schemes, the server, there are some variants of PIR where you can validate that the response that you got is an actual good element in the database. Like, you validate it against some commitment on the database and so on, but you could check that the server return some kind of like a valid response.
Well, so there was this recent paper that basically did, like, before encoding things in the matrix, did some like Reed-Muller encoding, and that's, well, you get basically malicious for a constant rate factor of expansion, but their pre-processing was not done by the server, right? Like, this code encoding had to be done by the client, and you can't.
Oh, you mean you need to encode the matrix separately by the client? Yeah, we can't. Or we have multiple clients doing this thing. I think in that work you require one client or one machine that processes the entire database.
Well, and the processing is hidden.
Yeah.
But I guess if you had a malicious PIR scheme with public preparation, you could solve this problem just by the server issuing queries and seeing our responses, right?
What do you mean by the server issuing? I mean, I guess if the server is malicious in this, like, okay, they can take down the system, not break privacy, but.
Well, but I'm just, if you had, right, so one way to check if the clients are responding honestly is for the server to
also issue queries and then see how they handle that. Yeah, you could do that. We were actually thinking of maybe having some kind of mechanism like that. The problem is the number of queries that the server has to issue is sort of proportional to the real queries that users have, right? So if there's one like server query, what we didn't manage to do is have the server send a few queries and then have an overwhelming probability of success.
And I guess what I said about malicious PIR, you don't even need it as long as the server remembers the
Right.
database while they're issuing.
Right. Okay. So I guess the last bit is we implemented this and we wanted to evaluate performance. So we used SEAL PIR, which is a library that implements PIR and built on top of it. We sort of envisioned this as being a messaging system or being used in the context of messaging. So we have 256 bytes messages. And then we used BGV's implementation from Microsoft SEAL library, which we slightly adapted to our APIs. Okay. So in terms of evaluation, I guess we wanted to check several matrices. So first, what is the setup time, right? So essentially, this means how often can you change a friend, and for how often do we need to, or should we cache these queries? Then we wanted to check communication latency. How do we scale with the number of clients? And what happens when our clients are sort of bandwidth limited, right? So if you're using this on a mobile device, for example. Okay, so we had some setup on our university cluster. And we did it so that one machine is the server, and then the other machines run clients on them. And this is, so basically what we have here on the x-axis is the number of clients that this server actually handled. So imagine you could deploy this with multiple servers, and each server has a replica of the database, but handles only a subset of the client's queries. So the way we evaluated it is basically, okay, we have a large database, right? So maybe it has 2 to the 16, to the 18, to the 20 messages, all stored on that server. And then on the x-axis is the number of clients the server is handling, basically the number of PIR queries it has, it needs to process, and the number of processing clients it can leverage, right? Okay. So the epoch setup time, you can see, is in the tens of seconds. So this means that you can't really change. Like, it's not like you can send a message and then like you keep changing peers. So ideally, we would have an epoch lasting like minutes, right? Because you want to sort of diminish that setup time. You want the actual communication to dominate.
Well, and what's the number of messages? You
So-
have like 100 clients, so
So why is this? You're asking, oh, why is this even dependent?
what is
Well-
the number of messages? Number of messages.
It's like the matrix size. So how many elements are in the server's matrix, right?
But expected is the clients per server. So how many clients do you have?
Well, okay. So these are relatively weak machines. That's like one thing. But you could imagine having. So remember when you said, okay, the names are kind of weird. Like maybe there is a distributed version where you could have multiple servers of handling the load, right?
Right.
So we wanted to evaluate. Ideally, we would have evaluated on 1 million users, right? But we couldn't. So the way we simulated this is basically we had a large database of messages, and then clients queried from that large database. So maybe you had 1 million messages in your database, and then a client queried from this million messages. So we ran up to 500,
500.
right? So we couldn't run 1 million. That was too much. Instead, what we did was we evaluated. So imagine that, okay, you wanted to support like 100,000 clients, let's say, then maybe you needed like 20 20 servers. Okay.
Okay.
Okay. So this is the way to read this. It's sort of the cheap way to evaluate, I guess, the system.
Okay. So the number of messages is supposed to represent the real number of clients.
Is the exactly. So think of it as yeah, that's the size of the matrix you query from. So the larger this matrix is, the bigger the query is.
Clients that you put on a physical machine. That's what we
Yeah, that the physical machine that this one machine handles. Yes. Yes. Exactly. Okay. So in terms of latency, well, here you have the same x-axis, which is the number of clients per server, the number of queries that the server needs to handle. The y-axis is the round latency, and we compare against two other systems, recent systems that are proposing to use PIR for this exact purpose. And so what you can see here is that there is a performance gap between distributed PIR and those other systems, and that the gap grows as the size of the database grows. So this is basically kind of showing scalability. Hopefully, this gap continues to grow even further the more messages you have. And this graph is sort of to a similar point. We just decided, okay, now we're going to have kind of a fixed ratio between the number of messages in the database and the number of clients that are querying data, right? So again, this is kind of, we wanted to be able to evaluate. Ideally, this would be one-to-one, but we couldn't do that. So essentially, the more clients you have, proportionally, the more messages you had in the database. And here you can see the kind of the asymptotic plays into effect.
So each client is doing O of users' work, right? So you're still doing the quadratic.
Yeah. No, we can't. We didn't get away with it.
Yeah.
Yeah.
Right, but it's just you're
But it's
over.
exactly. So we measure latency, and so that's like basically the bottleneck calculation. Okay, and the last thing is the impact of bandwidth, right? So those clients, they now need to receive jobs from the server, right? And that means that they need to communicate more. And so we wanted to see what happens when our clients are bandwidth limited. So we artificially limited the NICs to certain speeds. And so what you can see is that currently with our design, when the client has at least 40 megabits per second of communication, then having more doesn't impact performance. And so this is kind of roughly what we expect to need, at least with this workload. Okay, so that's the talk, right? So I presented distributed PIR and how it's being used for metadata private communication. We have an implementation. It's open source. Actually, I should have put the link probably here. And we investigated all sorts of scalability of this new protocol with our implementation. That's it. Yeah.
So sorry, I guess.
Yeah.
So I guess you actually, if you ignoring the efficient in practice question for a second, doubly efficient PIR would make this work so much better, right? Because then you would give each client the ability to answer certain queries, and you could they would all be doing sublinear work.
Right. So we wanted. That's like one of the future works we're currently working on is exactly this sort of things. How can we do this there are also other kind of proposals recently, right? So we wanted to see, okay, what happens if you have a scenario where you can use this amortized cost PIRs, and okay, maybe you could use that and distribute the load. That's like non-trivial to do. So we started looking into these things. Another direction we started investigating is whether we can reduce, kind of lower the communication costs. So there's a bunch more work that we're currently investigating with this. Yeah. Okay, thank you so much.